All right, hello everyone. Welcome to our first test review session of the fall semester. My name is Carter. I'm Studies Preceptor, joined also by Phyllis, one of our head course assistants. I'm super excited to be here today and to help you all go through some of the key concepts from this test. It is just about 7 o'clock, which is the time we said we would start the session. Or is it? Because on the course website, we said that we'd start at November 10th, 7 p.m. in quotes, direct characters, right? But on your computer, I would argue that actually, this isn't what's actually going on. We actually have this number on your computer, this Unix time, that's representing how many seconds have passed since January 1st, 1970. And so what time is it really is a great question that's going on right here. So if we're trying to represent this session start time right now, 7 p.m. on November 10th, well, I might say that this string is the best way to represent that. Like I could send an email, I could send a text that is saying November 10th, 7 p.m., those actual characters. But Phyllis, on the other hand, might say, well, this integer is actually more a better way to actually represent this because maybe it's more clean, right? But in talking about these different ways to represent this actual date, this actual time that we're in right now, well, these would lead us to different binary representations of this same date. So in the chat, if you'd like, how would this actually change our representation of this date, depending on if we held this date as a string or as an integer? What should we be thinking about as we go through and write some of these dates in actual machine language or machine code, this language computers speak? And go ahead and put some answers in the chat based on what you think. So one thing I'm seeing is that if we chose to represent this date as a string, well, we'd be dealing with maybe ASCII characters, right? ASCII characters, where each character would have its own code that we could put into binary. So for example, if I were to look at this string notation or the string representation of this date, well, that n there would be, not sure of the ASCII code actually, but the binary for that is 0, 1, 0, 0, 1, 1, 0. And I looked that up earlier, right? But this would be the ASCII or the binary representation of the ASCII number for n in November. Now, further, we go on to the O, and we might say, well, it's O, lowercase o specifically, is 0, 1, 1, 0, 1, 1, 1, 1. And that, again, is the binary representation for the ASCII value of this O character. But for this integer, right, this is a whole different way of representing that date. And so we might have to actually use something different. Here, we have this integer that is actually going to be a 32-bit number, or 32-bit represented with 32 bits, or in this case, let's see, 4 bytes, right? So this would be, and I'll type all of it out, but 0, 1, 1, 0, 0, 0, 0, 1, 1, 0, 0, 1, 1, and so on, all the way to having 32 bits that would show off this entire integer number here. So on Stack Overflow, I found this question of, if 32-bit machines can only handle numbers that go up to 2 to the 32, if we can only have numbers represented with 32 bits, how come we can write this number right here, this 1 trillion number, right? Well, I hope looking at this shows us that, well, actually, we're typing in the ASCII characters for this number and not necessarily storing it in 32 bits, right? There's a difference between representing things with ASCII and representing things with actual numbers. So these are all questions of representation, right? These get at issues of how we can store numbers, how we can talk about numbers inside of a computer. But what happens when, things might go wrong with representation? That's a big theme from this first week of the course. Well, let's say we wanted to add the year to our date, not just November 10th, 7 p.m., but November 10th, 7 p.m., 2021. And, we have 1,000 years until we're going to change from, 2000 to 3000, or even 100 years before we change from 2020 to 2100. So I think we'll be safe with just 2 digits, right? But as we go through, if we go sort of 21, maybe next year, 2022, and so on, well, we could get all the way to 98 and 99. And then eventually, right, we would hit this point where we can't count any higher. And we'd get this overflow, this transition from 99 to 0, 0, right? Because if we added 1 to the 9 on the right, we'd have to carry a 1, which would make it a 0, and then add this other 0 to the other side. And so, of course, we can only count up to 99. But then if we get to 0, 0, what year are we talking about anymore, right? Are we talking about 2000? Are we talking about 2100? We don't know anymore. And so we didn't have enough information to represent all of the possible years we could be talking about here. Now, that again is a question of overflow, this idea of running out of space to store the information that we're trying to store in this case. Now, the Unix time we talked about earlier will sort of came in to play here when we were talking about the January 1st, 2000, the Y2K bug, right? We went from basically 2 digits to store the year from 1999 to 2000, flipping back over. But again, this was sort of equivalent to 1900 and not 2000 in this case. But of course, we since sort of developed better ways to represent numbers now. And we have these 32-bit integers that can count even higher. But of course, we're running the same problem later on 19th of January, 2038. So maybe the key here is to use these 64-bit numbers that would give us much more space to represent all kinds of possible times here. But again, this gets at this idea of having a certain amount of space in the computer to represent our information. So certainly welcome here to pose questions in the chat if you have anything you want to talk about based on this representation question before we move on to some of these topics on like programming languages and so on. I'll just wait about a minute here for some questions to come in via the chat. All right, so I don't see any questions coming in, but definitely feel free to message them to me or to Phyllis, and we'll do our best to respond to them live. I see a question here. So what is Stack Overflow, right? There's this idea of going back to overflow. Well, we were talking about overflow in terms of representation of numbers, representation of digits here, but Stack Overflow can be somewhat similar in the sense that when we call a function in our computer, right, we keep putting the computer's memory higher and higher on that stack that we talked about earlier in week probably 4 or so. And as we keep calling more and more functions, we keep adding more and more memory, well, the stack only has a finite amount of space, right? And so if we were to climb all the way to the top of that stack, we eventually reach the top of that and run out of space there. So that is what's called Stack Overflow, the same idea of sort of running out of space to store the information we need to store. And another question is saying, can an integer be represented as high as 2 to the 31 minus 1? And in this case, that's actually correct if we have a 32-bit integer, right? If we have, let's see, I don't think I have an example of 32 bits here. I can go ahead and type one in. So here we left off at 1, 1. And let's go ahead and just add, let's say that's about 32 bits, right? We could theoretically represent numbers that can go as high as 2 to the 31 minus 1. If we were only caring about numbers that were positive or unsigned, they don't have a positive or negative sign in front of them. If we wanted to represent both positive and negative numbers, we'd only have half that many potential, half that much room to go away from 0, right? Because we're sort of dividing our space in half as we include both negative and positive numbers. Another question about Stack Overflow, I'm seeing, how would you know there is a Stack Overflow error? And would it say that there is one? I think most compilers would tell you if there is a Stack Overflow error, right? They're going to be running your code, going through, and in most cases, probably a recursion issue would happen. And so it can tell you, look, we've run out of memory. This is a Stack Overflow error. And certainly feel free to take other questions here. All right. So going back to this idea of running out of time, we have certainly enough time before this January 19th, 2038 to sort of think about how we can address this issue. And maybe part of that would involve thinking more deeply about programming languages, how they store data, and so on. So when we're talking about programming languages, one of the very first things that come to mind is this idea of a variable, storing information, right? In this case, we have a date. In this case, is pointing to this location memory of this actual integer representation of that date. But how did it get there? Well, that's where assignment in a programming language can come in. We have this equal sign, which is this assignment operator that can take whatever we put on the right and store it in a named sort of space on the left. So here we have this high number that's representing the date right now and storing that in this location that we're calling date, right? Now we could, if we wanted to keep track of the date, we could keep assigning new numbers to this date location. We could go ahead and give it the next second on, the next second on, and then so on. But a better way to do that is with these operators that are part of programming languages. And in this case, we have this operator that is just plus, right? We can add to current values that we have stored in our computer's memory. So here we have this operator that is first looking at date, the variable that is stored, reading from right to left here, and it's going to add a 1 to this location. So I might go ahead and add 1 here, and it's going to restore that value in that same location there. So these operators allow us to take certain data, manipulate it, and store it back in the same location. But what if we also wanted to ask questions about our data, right? Not just sort of store things and add to them and so on. Well, that's where conditionals can come in. And we saw these both in Python, in C, and even in JavaScript a little bit. Asking questions of our data. Is date greater than 0? Well, certainly it is in this case. So we get back this value of true. Or is date greater than maybe 2 million or 2 trillion? And in this case, well, it's not. And so we get back this false value. So conditionals are what help us sort of ask questions of our data and get back answers that are either yes or no, true or false, these Boolean values that we can talk about in computer programming. Now, that's okay, right? But what if we have something that we want to do that's, not just the single operation? So if we go back to our operators here, we've added 1, but since time keeps moving, time keeps going on, we want to actually be able to keep updating this time. And that's where this idea of loops can come in handy. So here we have this sort of English sentence of saying, I want to do something until the date is less than, let's say, 2 trillion here. And again, we're counting seconds from January 1st, 1970 in this case. So this combination of conditions or this implementation of conditions allows us to define this loop that can help us do something until this date reaches this certain state of being true. So here is basically what we're trying to implement in the terms of a while loop, right? We saw that this while loop can help us do something until a certain condition is no longer true, right? While something is true, we'll do that. But when it's no longer true, let's go ahead and break out of this loop and not do it anymore. Now, of course, there's more than a while loop, but most loops actually come from this very simple collection of conditions and these loops here. So if I go here to this next kind of loop, here I'm doing a few different things at once, right? I'm defining a certain value for date. I'm asking, is date less than, let's see, 2 trillion here? And if it is, I want to do something. And at the very end, I want to add 1 to our date. So here we're combining assignment in that first line there. We're adding conditionals in that second line. And on that fourth line, we're working with operators to add 1 to our date, right? But this is pretty much equivalent to a for loop, right? We could sort of combine all this into one place, which is what Python and C allow us to do when we have these different for loops. So again, thinking about programming languages here, the important thing is not so much this individual syntax of Python or C or JavaScript and so on, but more this idea of loops and building from those loops all the kinds of functions that programming languages can have. So thinking about this and using these as building blocks, a question for us in the chat is, Phyllis and I have developed this programming language that we've sort of shown so far, but we've only added this addition operator, right? I didn't show you subtraction, I didn't show you division or multiplication, but we actually want to be able to multiply things, right? We don't actually want to add them, we want to multiply them. And so if we can have variables, if we can have conditions, if we can have loops, well, what constructs could we use to actually make multiplication here? And I'll give you all about 2 minutes to think in the chat about what kinds of constructs from the past we can be able to use here to build multiplication into our programming language based on only the building blocks we've had so far. And I'll also look for questions as well if you would like to ask those too. All right, I'm seeing some answers come in. I'll give folks about a minute more. All right, I'm seeing some more answers, and a lot of these are talking about addition, right? We know we can do addition, and they're also talking about loops, right? if we sort of think about it, multiplication is really just addition, but looped, right? If we want to say, do 5 times 5, we would add 5 together 5 times, 5 plus 5 plus 5 plus 5 plus 5. And so in this case, we could actually have basically a while loop that is, or a few more variables here that could help us define, are we all the way through our number or not? But basically this idea of using loops to sort of add more to this sum that we're making for multiplication. All right. And again, any other questions here before we sort of move on to functions and talking about how functions and programs might work? Let's see. All right. I'm seeing a few and some I'll come back to even later. All right. So let's go ahead and move on to functions. Now, there's this idea that we saw at the very beginning of the course as functions as these like black boxes that take inputs and then give us outputs, right? But as I hope we've seen, these functions actually have pretty predictable elements. We can actually use these building blocks to make functions, including variables, assignments, operators, conditionals, and loops. These are all parts of functions and building blocks we can use to make our own functions. Now, when you're writing your functions in perhaps Python, for example, you use syntax like this, where you'd say, define a function called add time that takes two inputs, time and addition, and then gives us back or outputs time plus addition. So here I could give a certain time, like the start of the seminar, add maybe 30 minutes to it, and we'd arrive at maybe the time that we're at right about now, right? But the key thing here I want to highlight for you all is not necessarily the Python syntax, but this idea of these inputs and these return values. So here we have, again, our inputs of time and addition, and this return statement giving us back a value we can use later on in our program, right? So instead of inputs and outputs, maybe more specifically, we could say functions take arguments, again, that we've defined here, like time and addition, and they give back return values that we can say, or we can name with these return functions that occur in most any programming language, even in C, in Python, and so on. And these return values are different from side effects, for example, which are just things that sort of happen as the function runs. These return values are actually data we can use and later on incorporate into our program that these functions give back to us over time. Now, programs themselves can sort of be seen in a very similar way, right? When we're writing programs, especially sort of later on in weeks 2 and 3, we were talking about giving command line arguments to our programs. Well, in Python, defining the main part of our program is very similar to defining a function, right? We have this main function that is our program. And in this case, you'll see, well, we could use sys.argv and so on to get the command line arguments, but we have this very similar value of returning something. In this case, a status code to say, hey, we were successful, right? Returning 0 or returning 1 in those cases. So programs could be seen as a more general case of functions. They are functions themselves. They take command line arguments, which are their inputs, and they give us status codes as their outputs. And so what questions are there on functions and algorithms so far, before we move on to algorithms, that is? So good question. What's a status code? So earlier on in our programs, we were writing, we talk about giving a program a certain number of inputs. I believe for Caesar, for example, we were trying to give it maybe one command line argument that said /Caesar, the number of steps we wanted to rotate our key, right? So a status code can tell us, did our program function as we intended, or did the user use our program as intended? If we didn't give Caesar the right number of command line arguments, we might return 2 or might return 3 to symbolize, hey, this is actually not how you're supposed to use this program. And later on, thinking about web programming, talking about HTTP 404 errors, these are basically numbers that give us a clue as to what happened when our program ran. And so these are the outputs of our program that help us sort of interpret what happened as it finished running. And I'll also pause here just for a few more questions before moving on. All right, so programs themselves can, of course, implement algorithms. And that was our topic for week 3. Phyllis here is our expert on algorithms. So I'll turn it over to Phyllis to talk to us about algorithms.
All right, cool. We'll talk about some algorithms and have some fun thinking about how some algorithms, how much time they'll take, how much space they'll take. It'll be quite fun. All right, cool. Okay, so let's do a quick review about some of the sorting algorithms you might remember from week 3. The 3 that we'll be talking about today is bubble sort, selection sort, and merge sort. We'll talk about their best case, as well as their worst case, as well as how much space we might take. So just as a quick thing for bubble sort, let me come up with an unsorted list. So I will do 5, 0, 1, 2, and 1. So what bubble sort will do, you might remember we take a look at the first 2 elements and we notice that they are not in the ascending order we would like them to be in. So we're going to make a switch. And so we're going to switch them to be 0, 5, 1, 2, and 1. And then we look at the 2 elements, including this one that we just switched. And we notice they're not in the right place either. So we're also going to switch that over to 0, 1, 5, 2, 1. Similarly, we're just going to continue going down the line. So we switch those, the 5 and the 2. And then finally, we're going to switch that 1 and the 5. So this was the very first iteration. And what we did here is we went through all n of these elements and compared it to another, performing swaps as necessary. So for the first iteration, we took n total steps. And notice that this is not anywhere near sorted. This is actually not ascending order, surprising. So this actually will continue until this is in sorted order or whenever we stop making passes. And so can someone in the chat tell me what the worst case time complexity for a bubble sort might be? Okay, cool. We'll go with n squared, that is correct. So we'll go with n squared. And this is because we can make a total of on the order of n total passes in order to n total iterations to make sure that this bubble sort is sorted. And then if we consider the case where we have 1, 2, 3, 4, 5, where it's already sorted, then bubble sort will actually only take 1 pass because it's going to go through the entire thing and look, hey, this is already sorted, we're good. And then it's going to look at these 2, it's going to be like, oh, we're already sorted, we're good too. Or look at these 2, they're sorted. Or look at these 2, they're sorted. Since we did not make any changes in this pass, we are good. And so bubble sort's going to be like, all right, I'm done. And we only made n total checks. And so this is actually only going to take linear time for best case. So in best case, we do this big omega here, and it takes linear time. Cool. And then how much space does it take? Let's think about it. So in terms of space, if we are just making swaps, we don't actually take up any extra space. We're saying on the very first thing here, for example, we're switching the 5 and the 0. If you remember, that's 3 lines. We maybe have a temporary integer, and that's all we need in order to make these swaps. And since bubble sort is just a bunch of these swaps, then the space complexity is just going to be a bunch of constant things. And so the space complexity overall is going to be constant. So we'll say this is going to be the worst case is constant. Okay, so for selection sort, we'll use the exact same example, and we'll also use the first iteration. We'll have like 5, 0, 1, 2, and 1. And so if you remember what selection sort does is at every single point, it's going to look at the unsorted part of the list and find the minimum. So I'm going to, in my first iteration, go through the list and find the minimum. So I'm currently at 5. That's the smallest I have. I'm like, okay, the minimum is 5. And then we're going to go look at 0, and 0 is smaller than 5. So I'm like, okay, 0 is now the smallest. And then I'm going to go look at 1, it's not smaller than 0. Look at 2, it's also not smaller than 0. I'll look at 1, it's also not smaller than 0. And so then selection sort is going to note this is the current smallest, and I'm going to swap it with the beginning one. And so I'm going to get, after the first iteration, I'm going to get 0, 5, 1, 2, and 1. And so notice that we have to look through the entire thing to figure out what was the minimum. And so in that case, since we had to look through the entire thing to figure out what was the minimum, this took n total comparisons. And comparisons. And we'll have to do this every single time for n total iterations, because every single time, now that we're on our second iteration, we have to find the new smallest and move it here until we get to the very end. The nth one, we'll know that is the largest one. So the worst case for selection sort, you might remember, is O of n squared. And does someone want to send me in the chat what the best case for selection sort is? Awesome. Yes, it is n squared. And it's n squared because even though it's in sorted order, every single time we still have to go look for the smallest. So we still have to go through the whole thing to make sure that that value is the smallest. Just to solidify things, if we have 1, 2, 3, 4, 5, my thing is going to be like, oh, my sort is going to look for the smallest thing. So it's going to start with 1, be like, okay, 1 small, and I'm going to compare it to 2, and then compare it to 3, and then compare it to 4, then compare it to 5. And then notice 1's the smallest, so 1's going to stay here. But I have to do the exact same thing that I did before, because I still have to check if that is indeed the smallest. So the space complexity, or the best case time complexity, is going to be n squared. The space complexity is actually the same thing as bubble sort. Notice that all we're doing is a bunch of swaps. We don't actually need to store anything. So this is also going to be constant. And then in terms of merge sort, we get to exploit a very nice property of dividing our array into 2 parts and conquering. And so if we were to have this example earlier, 5, 0, 1, 2, 1, I would split it into 2 parts. So let's say I split it down here. And then now I sort the 2 arrays, 501 and then 2, 1. 501 can be split into 2 arrays again. And so let's say I do 5 and then we'll cut it here. And then I can split this again. But really, when I split this again, it's going to be a 5 and a 0. And then I'm going to merge them together. The array with the 0 is going to be smaller than that 5. And so we can put 0 and 5. And then when I merge this with the 1 here, I'm going to, running out of space. When I merge this with the 1 here, I'm going to realize, okay, so 0 is the smallest. And between 1 and 5, 1 is the smallest. I'm going to have 5. And then the same thing's going to happen on the right-hand side, where I'm going to have resorted to a 1 and 2. And then I'm going to merge these together to be the smallest out of these 2 arrays. The leftmost pointer for each, the smallest is 0. So I'm going to take out the 0, and then the smallest of the leftmost is 1. And I can mark out either 1. And then the smallest of this 5 and this 1 is also 1. So I can mark out this one. And then the smallest between the 2 and the 5 is going to be 2. So write down 2, mark this down. And then the smallest left, the only thing left is a 5. So that's how merge sort works. And the nice thing about merge sort is that every single time we keep dividing the array into. And so whenever we divide the array into 2 consecutively, this is going to take log n total of these like divisions. So it's going to be, worst case, it's going to be part log n, but in addition to dividing it, we also have to merge them together. And merging them together ultimately does take n total, because we have to make all of these comparisons. If you remember at the very end, we made all of these sorts of comparisons in order to merge them together. So it's going to be n log n. And just like selection sort, it doesn't actually matter what order it's already in. Merge sort will take these and still merge them together, still cut them all down into tiny pieces and try to piece them together. So the best case is also going to be n log n. And so finally, the space is going to be actually linear, because we have to copy this array, right? We can't just like chop the array in the space they already give us and make swaps, we actually have to store it somewhere else before actually being able to move them around. So this is going to take linear. So we're going to take a look at some examples of space and time complexity. I have an example here. It's going to be called a mega lazy sort. So in this sorting mechanism, I'm going to go through a list number by number. And when I see a number that is not in the right order, I'm going to throw it away because I'm lazy and it can't be a problem if it's not there. All right, so can someone tell me what the worst case time complexity is via chat in this particular example? Okay, we'll go ahead. Yeah, perfect. We'll go ahead and do something like the example that we did, but yeah, you're right, this is linear. So if we did a 5, 0, 1, 2, and 1, I'm lazy, I look at the 5, I'm like, okay, cool. And then I look at the 0, I'm like, 0 is not bigger than 5, I'm gonna throw it away. And then we're gonna check the 1, 1's not bigger than 5, I'm also gonna throw it away. 2 is also not greater than 5, we throw it away. The 1 is also not greater than 5, I'm also gonna throw it away. So basically I have a sorted array. Really, it's not sorted from the previous array, but this is indeed sorted. And I had to look through every single one of the elements inside this array in order to make this new 5 here. So for those of you that said linear, you're right. This worst case time complexity is O of n if there are n elements in this list. Cool. And so now we're going to do mega lazy sort, but with friends. So Carter and I are going to divide my list into 2 parts, and Carter and I are both mega lazy. So we're going to use that to sort our respective parts. And then I'm going to take the time to merge the 2 lists that Carter and I get. So does someone want to tell me what the time complexity for this is? We'll go ahead and get started and you can still message me. Yeah, so let's do 5, 0, 1, 2, and 1. And we're gonna divide it like this. And because I'm lazier than Carter, I'm gonna take the first half. Me. So whenever I sort this, I'm gonna write down a 5 and I'm gonna say the 0 is not bigger than 5, so I'm gonna throw it away. That's now my list, my new list. My sorted list. And then whenever Carter sorts his list, he's going to notice that there is a 1, and then there's also a 2. That's in the right order, but the 1 after is not in the right order, so he's just going to throw away that 1. And so this is now Carter's sorted list. Now I'm going to merge it, take the effort to merge it, and I'm going to notice that the leftmost on mine and the leftmost on his, the 1 is the smallest, so my final answer is going to have a 1. And then now that we've written the 1, we can take a look at the 5 and the 2, and then Carter's next smallest is a 2. And so we're going to get rid of that 2, and the last number left is a 5. So now I have a 1, 2, and a 5, and that's my final sorted array. And we'll take a look, and this is actually linear again, because whenever I did this sort, I had about half of the elements, and so I had to make a pass that took about n/2 total comparisons, and then Carter also did about n/2 comparisons. So if you combine the amount of comparisons that Carter and I did in the beginning, that's about n total comparisons. And then whenever I put our list together, whenever I merged it, there is a maximum of n total comparisons I have to make. That is assuming that I don't delete anything and Carter doesn't delete anything, then I would have to make a total of n total comparisons. And so the number of comparisons I have to make while merging is upper bounded by n. And so we have n, and for the original sorting, and then n for the merging, and that's going to be 2n. And remember, we can drop multiplicative constants for time complexity. So this is linear, or O of n. Cool. We will go to our next example. So next, I'm going to use internet sort. So I'm going to go through a list of A, B, C, D, and E. And first, I'm going to Google which is bigger, A or B. And then if Google says A, then I swap A and B. And then I ask Google about the next two elements, C, and whichever was larger between A and B. And then I make as many passes through the list as necessary to sort the list. So if you can send me in chat what sort of sort this reminds you of, that would be great. Give you a second to consider what sort this is like. Hint, it's one of those three sorts that we just talked about. Okay, so most of you, yes, it is bubble sort, in fact. Let's just run a quick simulation with the numbers that we had earlier. Let's have A be 5, B be 0, C be 1, D be 2, and E be 1. And then I'm asking Google which one's bigger, A or B, 5 or 0. Google's probably going to tell me that 5 is bigger. And so then I'm going to swap them to get this. And then I ask Google which one's bigger between C, which is this one, and whichever was larger between A and B. So this one, I'm going to ask Google, is 5 bigger or is 1 bigger? And Google's probably also going to tell me that 5 is bigger. So then I'm going to make this switch. And then I just keep going over and over until the end of this iteration. So I make as many passes through the list as necessary to sort the list. So I have here this first pass. And you might notice that this is in fact not sorted. And so I would have to make more and more passes until this is done sorting. And so this is the exact same as bubble sort. And the worst case time complexity would be just like bubble sort for O of n squared. And the space complexity is going to be constant because all I'm doing is making a bunch of swaps. Cool, nice, y'all. It is bubble sort. Okay, next we're going to do the very, very fun and not tedious sort of modified BOGO sort. I am brilliant at sorting, and I'm going to generate all possible permutations of a list and then store it in a list of lists. And then I'm going to check every single one of these permutations to see if it's ordered correctly. So if you could type in chat what you think the time and space complexity is, that would be great. And we're going to go for just a slightly smaller example this time, so I don't sit here for the next hour writing out the permutations. So let's say I have like 2, 5, and 1. So n equals 3 in this time. And I would have to write out every single permutation. So I have 2, 5, 1, 2, 1, 5, 5, 1, 2, 5, 2, 1, 1, 2, 5, 1, 5, 2. And then I'm going to go through every single one of them and see which of them are sorted. So 2, 5, 1, yeah, 5 seems greater than 2, so that's not it. Oh, sorry, 1 seems less than 5, so that's not it. Okay, and then this one, 1 is less than 2, so that also seems not it. 1 seems less than 5, that's not it. 2 seems to be less than 5, that's not it. And this one, 1 is less than 2, that's good. 2 is less than 5, that seems good. Cool, we found it. That did not take forever. So let's take a look. Each time we check one of these to see if it is actually a ascending ordering, we have to look at every single number. So when we check this one, we check, is 1 less than 2? Yeah. Is 2 less than 5? Yeah. So each time we check something, a list, it takes n comparisons. And then whenever we are making all these permutations, you might know the number of permutations is n factorial. And so the total amount of time it takes then is going to be n times n factorial, because for every single permutation, we're going to have to compare it. So that's the worst case time complexity. And then because I store it all in a list of lists, I have to store all of these. And so since there are n factorial permutations and each one takes n space, I actually also have a worst case space complexity or an actual space complexity of n times n factorial. So in this case, both of these are O of n times n factorial. Finally, we're going to go do a Zen sort. I'm achieving enlightenment now after writing out factorials, permutations of numbers, and I now have a list. And I realize that the list, like all things, is ephemeral and its order is insignificant. So I just leave it like that and I pursue enlightenment instead. If you want to send me how much time and how much space this might take, do let me know in the chat. All right, yeah, this takes constant time. In fact, it takes one operation. It takes me sitting here and quitting because I'm achieving enlightenment instead. So no matter how long the list is, I am going to realize that the list, like all things, is ephemeral, and I'm just going to quit. So it doesn't really depend on n. It's all just constant. I just sit there and I have to make that realization myself. And so the worst case time and space is just going to be constant time. Cool. Now we're going to talk a little bit about searches. So let's say I have an unordered list and I'm searching for a 5, and I want to figure out what is the fastest way to solve this problem. Can y'all send me in the chat what the fastest way to solve this problem is if I have an unordered list? Okay, so let's consider linear search. So linear search is going to require that I look through the entire list. And this is going to have a worst case of linear time because I have to go through every single one of them to search for a 5. And so in this case, we actually cannot use binary search because it's unordered. And so for example, if I was looking for a 5, 0, 1, 2, and 1, and let's say I was looking for, let's put a -1 here. Let's say I was looking for a -1 and looking for, I start with binary search, I go to the middle number, this is 1. So binary search tells me I should go to the left. And as you can tell, if I go to the left, I'll actually never find a -1, even though it exists right here. So for an unordered list, you cannot use a binary search. But for an ordered list, you can use a binary search. And the fastest way to solve this problem, oh gosh, is indeed binary search. Cool. All right. Any questions before we go on to recursion? All right, okay. So whenever we talk about recursion, which is a technique that allows us to continuously call on the same function or call on our own function, we're going to consider a few different things. So if you just send me a question, I will answer it later. We're going to consider the base case, which is when does the recursion stop? We have to define when the recursion stops, or else we'll get stack overflow because there's going to be too many functions being called in the stack frame. Won't be able to handle it, so we'll get a stack overflow. So when we stop the recursion, and then the recursive step is how do we call our own function? How to call own function. And the impacts on space complexity, like I said, every single time we make a function that goes into the stack. And so if we call this function infinite times and we don't have a base case, we're going to add to the stack infinite times, and then we're going to have a stack overflow. Just as a quick example, we're going to take a look at this function. I've called it nom. And whenever x is less than or equal to 0, I'm just going to return And then otherwise, I'm going to print nom and then return nom x minus 1. So if you could in the chat tell me what this prints and what its time and space complexity is, that would be great. But yeah, so for example, if we had like nom 3, this would print nom, nom, nom. Since nom 3 is going to go check x equals 3, and then it's not less than or equal to 0, and it's going to print nom. And then it's going to call nom 2, which is not less than or equal to 0, so it's going to print nom. And it's going to call nom 1, which is not less than or equal to 0, so it's going to print nom again, and then call nom 0. And then it's going to be equal to 0, so it's going to return, and then it will stop there. And so this, in terms of space and time, that's right, yeah. This takes linear time, linear for both. So for time at least, every single time I have a number, I do a constant time operation, and then I go to that number minus 1. So I just make n total of those constant time operations. And then in terms of the space, I make n total calls to the nom function, and since there are n total calls to the nom function, it's going to be linear. Cool. And so we'll do a quick problem. I hate climbing stairs. This is a true statement. And so I always have to make snarky comments when my friends have to flex their cool legs and climb up the stairs 1 or 2 steps at a time. And so let's suppose it takes n steps to reach the top of the staircase. And every time my cool friends can either climb 1 or 2 steps. And instead of climbing stairs, I like to think about how many distinct ways my friends can climb to the top. So there are multiple ways to solve this. We'll talk about both ways. The first way is to use recursion, and the second one is more of an iterative solution where we build up to a answer. So for recursion, we will write a function in Python, and we'll call it climb stairs. And it's going to take a number n, that's the number of floors. And so let's do first component recursion we talked about is a base case. So we want to check if n equals 1. If n equals 1, that means there's 1 stairs. There's only one way to go about it. No matter how cool my friends are, they can only take 1 step. So then we're just going to return 1. If there are 2 steps, my friends can be cool, go up the 2 steps in one go, or go up the 2 steps one at a time. There are 2 ways to do it, so we're going to return 2. Otherwise, we can think about it like if there are 3 steps, then they can either take 1 step and then make the 2-step hop, or they can take, or they're on the 2nd step and they make the 1-step hop. So really it's just, otherwise we can return climb stairs n minus 1 plus climb stairs n minus 2. Think about if we're on the nth step, then they can either take 1 step from the n minus 1, or they can take that 2-step hop from the n minus 2 step. And we will think about the iterative solution really quickly. And then if you have questions, I can answer them afterwards. So the iterative solution is building up towards that answer. So earlier we said if there are n steps, I want to think about the n minus 1 step and the n minus 2 step. The iterative solution lets us think about how do I get 1 step? How do I get 2 steps? How do I get to 3 steps? How do I get to 4 steps? All the way up to how do I get to n steps? So instead of going top down, we're going to go like from 1 to n. So let's write another solution where we have another climb stairs function, just like earlier. And we're also going to do like if n equals 1, same thing. We want to go ahead and return 1. And if n equals 2, we're going to go ahead and return 2. And then in order to store all of this information, like 1 all the way to n, we're going to have an array. I'm going to instantiate this array with some zeros. This is some syntax that you might not be familiar with, but we can talk about later. But essentially, this just gives me n zeros. And then we're going to say this particular answer, the zeroth one, or in this case, since it's zero indexed, the first step there's only one possible way to do it. And the second step has two possible ways to do it. And then we can do a for loop. So for the rest of them, what I can just do is look at the two before. So just like I did earlier, where I did n-1 plus n-2, I'm going to just populate this array in the same way. So answer I is going to be answer I-1 plus answer I-2. And at the very end, all I have to do, since I computed it from 1 to n, all I have to do is return that last number, which is going to be the n-1 index. Okay. Any questions on that, we will answer shortly. But I'll hand it back to Carter.
So for our last about 10 minutes here, we thought we would do some practice with practice questions from the past test. And so we'll go ahead and open two breakout rooms. One will be for practice with programming constructs, and there's a prior test question called programming in B that might be useful there. And then for more practice with complexity, we'll have this past test question called complexities of a space that again might be useful there. I think Phyllis will be able to sort of help in the complexity breakout room. I'll be able to help in the programming constructs breakout room. And we'll certainly be able to be here until about 8 o'clock or so. But the goal here is to give you practice with some of these past test questions. And certainly happy to answer any questions that you all have in the moment from the past algorithms work as well. All right, I think that's going to conclude our review session. So we're going to go ahead and do some practice with past test questions.